This is part 2 of the lecture on backpropagation. Backprop computes the derivatives of the divergence between the actual and desired outputs of the network for any input with respect to all of the parameters and the variables in the network. We've seen this. In the first part of this lecture, we computed it term by term, treating each neuron and each weight individually as scalars. For layered networks, the entire operation is much simpler to comprehend if we think of the process in terms of vectors. This results in simpler arithmetic. Also, if we implement it as vectors, we can take advantage of fast matrix libraries to make the computation faster. So let's restate the entire process in vector terms. In fact, this is what any real system uses. Let's begin with some definitions. Consider the kth layer of any network. So you have some kth layer, and this receives its inputs from the k-1th layer. Now, let's write the affine inputs to the kth layer as a vector. So over here, let me write zk is the vector of affine inputs to the kth layer. So this is the affine value for the first neuron, the affine value for the second neuron, and all the way down. Let me write the output of the k-1th layer also as a vector. So I can say yk-1 equals y1 of k-1, y2 of k-1, and so on. And now let me write all the weights of the which connect the k-1th layer to the kth layer as a matrix. I'm going to write wk is this term here. I'm going to it's w11k, w21k, w31k, and so on. The second layer is w12k, w22k, w32k, and so on. And I can continue to fill in the weights matrix. Now observe that the first row over here represents the set of weights to the first neuron in the kth layer. The second row over here represents the set of weights to the second neuron. In general, the jth row of this matrix represents the set of weights to the jth neuron. Now, I can also, each of these neurons also has associated with it a bias. Let me write those bias terms also as a vector bk, which is going to be the bias for the first neuron in the kth layer, the bias for the second neuron in the kth layer, and so on. Now, when I write it like this, then we can just write zk equals wk times yk-1 plus bk. Now you can see why this will work. Consider the first. Well, let me actually expand this equation out, and you can see why. What I'm really writing, I will stop writing the superscripts for convenience. I'm writing z1, z2, and so on is going to be w11 W21, W31, etc., W12, W22, W32, etc., and so on, times this is the set of y's from the previous layer, y12, y13, etc., plus these are the sets of biases for the kth layer, v1, v2, etc. You can see how this works. Z1 equals W11 times Y1 plus W21 times Y2 plus W31 times Y3. All the way aside, you'd be weighting each of the y's with the appropriate weight and summing them up, and finally summing the bias for the first neuron. So this would hold true for any z. In general, the jth row of the z entry is going to be, I'm not sure why these things keep disappearing. The jth row of the z entry is going to be the product of the jth row of the matrix and the outputs of the previous layer plus the jth bias. So, and because the jth row of the weight matrix is the set of weights going into the jth neuron, this entire operation, as you can see, will give you the correct affine value for the jth neuron. I apologize for these pictures which keep disappearing. This seems to be a problem with the tablet that I'm using. So what we see from all of this is that when I write things out in this manner, then for any particular layer of the network, I can write out a weights matrix where the jth row of the matrix represents the set of weights going into the jth neuron. And if I write out the output activations of the previous layer as a vector yk minus 1, then I can write zk equals wk. The subscript k means that it's the weights matrix for the kth layer times yk minus 1 plus bk. So this entire operation of computing these affine values for the kth layer gets compressed into this little algebraic equation. And then once I compute the affine combinations for all of the neurons in the layer for the kth layer, I can apply the set of activations for the kth layer as one single vector operation to compute the vector of outputs for the kth layer. So once you write things out in this way, in this very nice compact vector notation, then the entire forward and backward operation becomes very simple to write. Let's consider the forward operation. We begin by setting y0 as the input. Then first, we compute the affine value for the first layer, which is z1 equals the weights matrix for the first layer times y0 plus the bias vector for the first layer. Then we compute the output vector for the first layer, which is simply obtained by applying the first layer activations to the affine vector at the first layer. And then you compute the affine vector for the next layer by using the weights matrix and bias for the second layer. And then you compute the output of that layer, and so on until the affine values for the last layer, from which we can compute the output of the network. So here is the entire forward pass. You first set y0 as the input, then you loop through the layers. For each layer, first you compute the affine vector zk using this very simple formula, which utilizes the weights matrix for the layer and the bias vector for the layer. And then finally you apply the activation function for the layer to compute the outputs of the layer. The output of the final output of the network is the output of the last layer. And so here is the pseudocode. It's the same operation written in pseudocode. You initialize y0 as x, you iterate through the layers, and within each layer, first you compute the affine value and then the output of the layer. The final output is the output of the last layer. So we've got the forward pass. This was very easy, and the code is very simple when you write things out as vectors and matrices. I apologize for wiping my nose. It's coming for some reason. Now we must compute the backward pass. The entire network is actually a nested function. First, we compute an affine function of the inputs. Then we apply, which is out here. Then we apply the first activation to this affine function. Then we compute an affine function of the outputs of this layer. Then we compute the second activation to this affine function, and continue to compute this operation till we find this sequence of operations until we get the output of the final layer. So this is a nested sequence of operations. Going forward through the network from the input to the output is the same as going from the innermost function to the outermost function in this nested function. Similarly, going backward through the network is the same as going from the outermost function through to the innermost function. Now, the divergence computed on the output of the network operates on the output of the network Fn. So the divergence function too is a nested function. At this point, we need a few more calculus definitions. First, consider a I'm having some trouble here. Okay, now consider a scalar function y1 of some variable z. Then the derivative of y with respect to z is simply going to be, and let's say z is a vector, which z is a vector which of the form z1 through zn. Then the derivative of y with respect to z is simply going to be a row vector of the partial derivative of y1 is going to be a row vector of the partial derivatives of y1 with respect to each of the components of z. And we know that when we use this definition of the derivative, then delta y1 equals this derivative times delta z. Now consider a second variable y2, which is computed using a different function f2 of the same variable z. Then the derivative of y2 with respect to z is going to be a row vector of partial derivatives. Partial of y1 with respect to z1, partial of y2 with respect to z2, and so on. And once again, you're going to get this equation, delta y2 equals the derivative of y2 with respect to z times delta z. Now, so if I stack y1 and y2 together into a vector y, then the derivative, any delta y, is going to be delta y1, delta y2, which I can write as the partial derivative of y1 with respect to z1, partial derivative of y1 with respect to z2, etc., stacked on top of the partial derivative of y2 with respect to z1, partial derivative of y2 with respect to z2, etc., times delta z. This is just stacking these two equations one on top of the other. So in other words, delta y equals this matrix, which I will call the Jacobian of y with respect to z times delta z. And so this Jacobian, in fact, is the derivative of this vector y with respect to my variable z. So when I have a function y equals f of z, then the derivative of y with respect to z, which is this Jacobian, is this matrix where the rows of the matrix consist of the derivatives of the individual components of y with respect to z stacked on top of one another. And so here you can see how this works out. If y is an m component vector and z is a d component vector, then the derivative of y, the individual y's, is going to be a 1 cross d row vector. So the Jacobian itself is going to be m cross d. Now, so hopefully this explains what the structure of the Jacobian and where it comes from. Now, if you have a network in which you have an activation function which operates on this affine combination and produces the outputs, and the activations are a set of scalar activations, then each y only depends on the corresponding z. The y doesn't have any dependence on the other z's, so the derivative of any y with respect to the other z's is 0. So the Jacobian matrix over here is going to be a diagonal matrix where each diagonal entry is going to be the derivative of the corresponding y with respect to its own z. So this is simply going to be a diagonal matrix where the diagonal entries are the derivatives of the individual activation functions. Now, if we have a vector activation, then each y depends on every z. And so then each y is going to have a non-zero derivative with respect to every z, so the Jacobian matrix will be a full matrix. Now we have a special case over here. Let's say z is an affine function of y. So z equals some w times y plus b. Then you can see easily enough that if I have z equals wi plus b. Now let's say z is a n cross 1 matrix vector. Y is a m cross 1 vector. So w has got to be n cross m. Now, if I increment y by delta y, the resulting output is going to be w times y plus delta y plus b, which is going to be wy plus b plus w delta y. So the increment in z is going to be w delta y, which means that the derivative of z with respect to y is simply this W matrix. So the Jacobian of z with respect to y in this kind of a relation is simply going to be this matrix W. Now you can also check the size over here. Z is n cross 1, b is m cross 1. So we know that when I take the derivative of this guy with respect to b, that derivative has to be n cross m. And check the size of W, that is indeed n cross m. So it matches. This is an m, this is an n. I'm having trouble writing on my tablet. So the sizes will match. You can also compute the chain rules for derivatives. So let's say y is a nested function of x. So y equals, again, let me write this, hopefully this works. So y equals f of z of x. And let's say y is an n cross 1 vector. Z computes a k cross 1 vector, and x is an m cross 1 vector. Then eventually y is a function of x. So the Jacobian of y with respect to x must be n cross m. This much we know. Now the chain rule says that the derivative of y with respect to x can be computed, which is actually a Jacobian, can be computed as the derivative of y with respect to z times the derivatives of z with respect to x. Now note the order of multiplication. So if actually now these derivatives are Jacobians, so the Jacobian of y with respect to x is going to be the Jacobian of y with respect to z times the Jacobian of z with respect to x. Now note the order of multiplication. As you go from the outside to the inside of this nested function, you keep right multiplying. So first you encountered z, that gave you the first derivative. Then you encountered x, that gave you the second derivative. So as you go into the nested function, the derivatives keep right multiplying. And you can also check the sizes. Now we know that this guy must have size n cross m. Now the derivative of y with respect to z, which is n cross m and n cross k, is going to be n cross k. And the derivative of z, which is k cross m, which is a k component vector, with respect to x, which is an m component vector, is going to be k times m. So this entire operation is going to give you n times m, which is indeed what you want. So you can see that the size is split, but you can also verify this mathematically. I have y equals f of z of x. So I can write, so delta y equals the Jacobian of y with respect to z times delta z. That's what we get from this, from the outer equation. And from the inner equation, we get delta z equals the Jacobian of z with respect to x times delta x. So if you combine the two together, you're going to get delta y equals the Jacobian of y with respect to z times the Jacobian of z with respect to x delta x, which tells me that this term over here is the derivative of y with respect to x. So you get the chain rule right out. So that's basically what we've got over here. This also holds for, now this holds when I have a nested function where the output is a vector. This also holds when the output is a scalar. So for example, if I have d, which is a scalar, is some function of z of x. And again, as before, if I have, say if I have, say, z belonging to k cross 1, and say x is m cross 1, d of course is a scalar, then the derivative of d with respect to z, so d equals f of z, so the derivative of d with respect to z, d being a scalar, is going to be 1 cross k. the derivative of z with respect to m is going to be a k cross m vector. So when you multiply these two, you're going to end up with a 1 cross m vector, which is indeed what the size of the derivative of d with respect to x must be. Now, so the equations themselves say that the derivative of d with respect to x is going to be the derivative of d with respect to z times the derivative of z with respect to x, which is going to be the Jacobian. Again, the order is important. As you go into the function, the innermost derivative always right multiplies. And we've just seen that this relationship gives you the correct size for the derivative of d. And also you can once again see that mathematically that this relationship holds. Delta d is going to be the derivative of d with respect to z times delta z. And delta z is going to be the derivative of z with respect to x times delta x. Plugging this guy here into this equation gives you this equation at the bottom. Delta d equals the derivative of d with respect to z times the Jacobian of z with respect to x times delta x, which tells me that this term over here is the derivative of d with respect to x, which is basically what we got in the chain rule. Again, the key point is that as you go into a nested function, outside to in, as you keep progressing into the function, the latest innermost function provides you a derivative which must be multiplied to the far right to give you the overall derivative of the output of the function with respect to the variable at the nesting level that you currently are at. We also so there's one final relation to consider before we're all set. Let d be a scalar function of wy plus z. This again is a nested function. I can write d equals f of z, where z equals wy plus b. So again, using the chain rule, the derivative of d with respect to y is going to be the derivative of d with respect to z times the derivative of z with respect to y. So, which gives you this equation over here, the derivative of d with respect to y, which is the derivative of d with respect to z, times w. W because the derivative of z with respect to y, as we saw earlier, is simply the matrix w. So this is something that's easily enough derived. Now, where am I? Yeah. Now, if I compute the derivative of d with respect to b, I can use the same chain rule. That is going to be the derivative of d with respect to z times the derivative of z with respect to b. But the derivative of z with respect to b is just an identity matrix because there is no additional term multiplying b over here. So the derivative of d with respect to b is simply going to be the derivative of d with respect to z. So this is easy. The final bit is this guy over here, which is the derivative of, let me see if I can. So I have d equals, what is happening? Ignore this. So I have d equals f of wy plus b. I'm saying z equals wy plus b. So d equals f of y. F of z. So the derivative of d with respect to w using our chain rule is going to be the derivative of d with respect to z times the derivative of z with respect to w. Now this is an ugly looking equation, but then and the math is a little tedious, but eventually this just ends up working out to be y times the derivative of d with respect to z. It's an astonishingly simple result. But then let's see how this works. Now, in general, when I have a function, a scalar, d equals some function g of some w, for any function g. If w is of size n cross m, then the derivative of d with respect to w is going to be of the size M cross N. It's the transpose. This is a standard property. And we specifically saw that when W is a vector, M would be 1, and this actually holds. So let's see if this indeed holds here for this vector, for this matrix, and for this relationship, right? So we want to have, let D is a scalar, let Y be, let's say Y is a M cross 1 vector, and let W be an N cross M matrix. So what this means is that Z is a N cross 1 matrix because you're multiplying W and Y. And so the derivative of D with respect to Z is going to be a 1 cross N row vector. So when you have Y times the derivative of D with respect to Z, this is going to be a M cross 1 column vector times a 1 cross N row vector, which is an M cross N matrix, which is basically what we want the size of the derivative of D with respect to W to be. So we see that this relationship over here holds. The derivative of D with respect to W is simply Y times the derivative of D with respect to Z. Now there's a different way of visualizing it, which is much more useful to us. So let's say in a network, I have some set of Y's which are being operated on by a matrix W to give me some affine value Z, and that assume that all of these Z's eventually are used to compute a scalar value D. Then the derivative of D with respect to W is going to be Y times the derivative of D with respect to Z. And this is just going to hold. All of the equations that we just saw sum to this little property here. And this is something that we're going to have to remember. Once we have all of this, we have everything we need. So here is backprop. I'm going to use this notation nabla yz to represent the derivative of y with respect to z in a generic sense, just for the purpose of illustration. So let's say we've performed the forward computation. We have the output of the network. We have computed the divergence. First, we compute the derivative of the divergence with respect to the output of the network. If the output is an n-dimensional vector, then y is n cross 1. So this derivative is going to be 1 cross n. The actual derivative is going to depend on the nature of the divergence function. Now that we have gotten here, we can take a step back and compute the derivative with respect to the affine values at the output layer. Now remember that going backward into the network is like going into the nested function. That means that to compute the derivative of the divergence with respect to this guy, I must right multiply the derivative of the divergence with respect to y by the derivative of y with respect to z. And this derivative of this y with respect to z is simply just the Jacobian of this final activation. Again, we can verify the sizes. So we have y is a n cross. I have no idea what is going on. So we have y is an n cross 1 vector. So the derivative of the divergence with respect to y is going to be 1 cross n. The Jacobian of y with respect to z is going to be an n cross n matrix. So the derivative of y with respect to the divergence with respect to y times the Jacobian of y with respect to z is 1 cross n times n cross n, which is 1 cross n. So this gives you the correct size for the derivative for this for the z. Then we take a step back and compute the derivative with respect to the output of the previous layer. Using the chain rule, this is simply going to be the derivative of the divergence with respect to z, right multiplied by the derivative of z with respect to y. And this derivative of z with respect to y, again, remember, z is, the relationship for z was z equals w y plus b, remember? So this implies that the derivative of z with the Jacobian of z with respect to y is simply w. So we know this. And therefore, this term over here is simply going to be the weight matrix. And so the derivative of the divergence with respect to y is the derivative of the divergence with respect to z, this is z, times the weight matrix over here. And now, using the other rules that we just discussed, which hopefully I can find. I have no idea. Somewhere here. So when you have this kind of a relationship where y is operated on by a matrix W to compute z, then we saw that the derivative of the divergence with respect to W is y times the derivative of the divergence with respect to z. So I can just use that relationship out here and say the derivative of the divergence with respect to this weight matrix is going to be the y over here, yn minus 1, times the derivative of the divergence with respect to zn. Both of these terms are available, so now I can compute the derivative for these weights. So also, the derivative of the divergence with respect to these biases is simply going to be the derivative of the divergence with respect to the z. We've seen that too. So and so now we have the updates for the weights and biases at this layer as well. Again, it's very easy for us to verify if you actually go through the arithmetic that the size of this derivative is going to be the transpose of the size of this matrix, or the size of the transpose of this matrix. Now we can take a step back and continue to use the chain rule and compute the derivative of the divergence with respect to the affine inputs to this layer. That's simply going to be the derivative of the divergence with respect to y times the derivative of y with respect to the affine term, which is simply the Jacobian of this activation function, of these activations. The Jacobian matrix for this layer is going to be diagonal for scalar activations. And then we can go back and compute the derivatives for the output of the previous layer by using the chain rule again, which is going to give me that the derivative of the divergence with respect to this term is the derivative of the divergence with respect to this z times the derivatives of z with respect to y. And the derivative of z with respect to y is simply the weight matrix for this layer. And so we have managed to compute the derivatives out here as well. And then again, using this rule that we just saw, I can also compute the derivative of the divergence with respect to the weights here, which is simply going to be the y value here times the derivative for the z values here. And the derivative for the biases is simply going to be the derivatives for the z values here. I'm just reusing the same equation I used on the next layer, but now applied to the variables at this layer. And then I can go back. I can keep going back all the way until we get the derivatives for the first hidden layer affine values. And from that, we get the weights derivatives for the weights and biases for the first layer. And if we want, we can even go back and compute the derivatives for the input. And so here is the entire backward pass in pseudocode. First, you compute the derivative of the output of the network, of the divergence with respect to the output of the network. Then you compute the Jacobian of the output layer. Then you go back through the layers, and in each layer you first compute the derivative of the divergence with respect to the affine values by right multiplying the derivative of the divergence with respect to the y values by the Jacobian of the activation, and then go back and compute the derivative of the divergence with respect to the previous layer outputs by right multiplying this derivative by the weight matrix. Along the way, we can also compute the derivatives for the weight matrix and the bias vector itself using the formula that we just saw. And so here is the pseudocode for the entire training process. We initialize all the parameters and then we iterate. Within each iterate, we first set all of our derivatives to 0. Then we go through the training instances. For each training instance, we first pass the training instance through the network to compute the output of the network, as well as all the intermediate values. We compute the divergence, and so we can add the divergence to the loss. Then we perform backpropagation. We go backwards through all of the layers, and for each layer, we compute these intermediate derivatives with respect to the outputs and the affine values for the layer, and also compute the derivatives now for the weights and the biases for the layer. And we accumulate these. We accumulate these derivatives. Finally, when we are done with the entire training data, we normalize these accumulated derivatives by the number of training instances in the data, and apply these normalized derivatives within the gradient descent rule to update the parameters. We continue these iterations until the loss is converged. And so when we set up for a problem, here's what we do. If we were setting up for digit recognition, our training data is going to be of this kind. You're given the problem will be to recognize a binary classification problem, to recognize whether an instance is the digit 2 or not. So you'd have a network of this kind with a simple sigmoid activation. The output is going to be either 0 or 1. In this setting, you'd have training data of this kind, images of various digits, and a label telling you whether it's indeed the digit 0 or not. We saw that we would use the Kullback-Leibler divergence in this setting. We would pass each training instance through the network, propagate it backwards, propagate the derivatives backward using backpropagation, and compute the derivatives for all of the parameters in the network. We'd accumulate these derivatives over all of this data and apply it within gradient descent to learn network parameters. If you had a multi-class classification problem, now the network is going to have multiple outputs representing one representing each of the classes. So if this was a digit recognition task, the network would have 10 outputs if you were trying to recognize the digits 0 through 9. And if you wanted to have both 0 and O, then you would have 11 outputs. Or you could have 11th output saying none of the above. Either way, we'd have a network with many outputs. The output layer itself is going to have a softmax activation. The ideal output is going to be 1 hot. When we would pass each training instance through the network, you get the output of the network, you compute the KL divergence between the output of the network and the ideal output, and then propagates its derivatives backwards through the network. You would do this for all of your training instances, accumulate all of the derivatives, compute the average derivative from all of them, and use those within gradient descent to updates to learn the network. So that is the entire training process. And so here's the story so far. Neural networks must be trained to minimize the average divergence between the output of the network and desired outputs over a set of training instances. Minimization is performed using gradient descent. The gradients of the divergence with respect to network parameters can be computed using backpropagation, which requires a forward pass of inference for each training instance, followed by a backward pass of gradient computation. And the computed gradients can now be incorporated into gradient descent updates to learn the parameters. So we've seen the entire training process in summary. But then, does it work? How fast is it? Remember, this is an iterative descent algorithm. How quickly does it get to the solution? Does it actually get to the solution? And when it does get to some kind of a point, does the answer it gets actually generalize to other data which are not part of the training data? What exactly do these outputs mean? Do these outputs mean? And what does generalization really mean? Many questions. And so we will deal with that in the next few lectures. In the next lecture, we are going to deal with the issue of convergence and generalization. Thank you.